Hello everyone, I'm excited to share the first paper in the Moment of Seismology and Tectonics series. We all know that 2020 will be a historically special year. For me, 2011 is also very special. I finished my master's program and started my PhD at Indiana University that year. It is also special in seismology. The Tohoku earthquake, like magnitude 9 earthquake, shook the entire world and the seismology community in many ways. In the same year, there was a magnitude 5.8 earthquake in Mineral, Virginia, in the United States. Globally, there are many earthquakes with different sizes occurring every year, even every day. An interesting question to ask is whether we can predict the final size of an earthquake by the appearance of the first few seconds of the earthquake. This is the topic of the paper that I'm sharing with you today. Today I'm sharing with you the paper by Satoshi ID published in 2019 on Nature, combined with the commentary wrote by Rachel Abercrombie. The paper addresses the similarity of the stars of big and small earthquakes. Like in many other places around the globe, there are numerous earthquakes occurred along the Japan Trench, some of which were very devastating. The author examined the earthquakes along the Japan Trench occurred between 2002 and 2011, before the 2011 Tohoku earthquake. The beach balls in the left figure are subduction type earthquakes. Those in the right figure are other type earthquakes. The green dots are seismic stations that recorded these earthquakes. The author found that nearly 20% of the co-located large-small earthquake pairs have starting waveforms with higher than 80% similarity. The figure here shows the stars of the earthquake P waves at different stations for two earthquakes. The black wiggles are waveforms from the larger earthquakes with magnitude 4.7, while the red wiggles are waveforms from the smaller earthquakes with magnitude 3.9. The first 0.2 seconds of the earthquake waveforms are almost identical between these two earthquakes. To explain the high similarity of the stars between large and small groups, the author proposed a model with a cascading rupture propagation. In this model, the feeder starts small but grows into a bigger rupture zone. The most important point is that in this model, the rupture for small earthquakes appears very similar to that for larger earthquakes, just with different scales. This is also called a fractal feature. So here's a simple message from this paper. It seems difficult to predict the final size of an earthquake by only looking at how the earthquake starts. However, there are two very important issues to get that conclusion from this paper, as noted by Rachel Abercrombie in a commentary. Firstly, the author only analyzed the high frequency data, missing information on the characteristics of the waveforms at lower frequencies. This is a very critical issue considering the frequent occurrence of slow slip events at subduction zones and low frequency earthquakes. Secondly, when earthquakes were categorized into the large and small groups, they have relatively small size gaps. That is to say that there are about 60% of the events pairs with magnitude difference of only less than 1.5. So, in summary, this is a very interesting paper, shedding light on the predictability of earthquake sizes, excluding repeating earthquakes. I look forward to further studies in this direction that hopefully would fill the gaps outlined in the commentary. So, thank you for watching this week's Moment of Seismology and Tectonics. See you next week.